everyone. So, welcome to the nth week of Galhotra. We have an exciting speaker, exciting topic. So we welcome Sainyam, Galhotra, who is an assistant professor at Cornell University, working in that exciting topic of responsible data science. Sainyam has had a lot of awards under his belt that you all see in the bio, things like the FSE Best Paper Award, as well as Artifacts Awards as well. And today he's going to tell us all about responsible data science. So join me in welcoming Sainyam.
Thank you everyone for the introduction. Thanks everyone for coming. I know it's Thanksgiving next week, and it's a Friday, so thanks everyone. So I'll start this talk with a personal story, but feel free to stop me at any point if you have any questions. So back in 2014, I used to work at Xerox Research Center in India, and we had a client which was a real estate investor in the city of New Delhi. This client approached us and said, "We have a bunch of houses. We are trying to figure out which ones to buy, which ones to sell. Can you help us make that decision?" So we thought, let's look at the data that they have. So we looked at the data. The data looked something like this. It had the address of the house, year of purchase, area, rooms, bathrooms, zip code, and current price for some subset of that. And the goal was to fill in this last column for them so that they can make an informed decision for the problem. We thought it's a simple machine learning problem. Let's train an ML model. It'll be done in like 2 days. We did exactly that. We used the data set, trained an ML model, tested on a validation set. The accuracy of this ML model was very poor. It was around 0.65. This was not a good model that we could deploy in practice. So we were again back to the whiteboard discussing what can we do. After a few discussions, after going back to the investors and discussing with them, we asked, how do you predict price of these houses? So what they said is, we often look at other features like distance from park, access to high-speed internet, and so on. So what we did was, we collected additional data sets about distance from park, access to high-speed internet, combined with the original data set, retrained the model accuracy went up by 18%. So this was something promising. We were getting slightly better results by adding additional data sets. Further, we noticed, you may see in row number 2, there's some missing values in the data set. There is noise, there is heterogeneity. If we clean the data set, do missing value imputation, fix the data set, and retrain the model, the accuracy went further up to around 92%. And this was a good model that we shipped in at the end, and they were happy with our model. So in summary, we came up with a complex data science pipeline, which consisted of 3 main steps. The first was data discovery, which aimed to choose the best data sets for the problem. Data preparation, which focused on missing value imputation, data cleaning, outlier detection, and so on. And data analysis, which was the task to train the best ML model. This whole process we had thought would take 2 days for us because it's a simple ML task. But in reality, for 5 of us, it took around 3 months to train the ML model. There was a lot of discussion and brainstorming about what methods to use, which ones to use, and why. And I was so frustrated at the end that I resigned to do a PhD on this topic. So after this successful deployment, the director approached us and said, "You have worked hard for 3 months. Do you want to sell this as a service to other clients, other companies in the country?" We thought that was a great idea. So we got data from another client from the city of Mumbai, completely different city, to avoid conflict of interest. We did the same steps. We combined with distance from park, access to high-speed internet, performed the same steps of cleaning, trained the same ML model. The pipeline failed. The pipeline was again performing terribly, even though we used all our knowledge, whatever we had learned from the city of New Delhi. The reasons of failure were many, but let's look at some of them. First, rather than distance from park, distance from beach was a better predictor in this case because Mumbai is closer to ocean, which New Delhi was not. Additionally, the data set from Mumbai had heterogeneity. For example, the area of the house was mentioned in square feet and acres, whereas our pipeline assumed everything is in square feet. So whenever something was in acres, it thought it's a very small house, but actually it was a very big house. And additionally, we had to retrain the machine learning pipeline, figure out the best hyperparameters for that pipeline. So because of all these reasons, this data science pipeline failed the moment we changed the initial data set. The moral of the story is traditional data science pipelines fail to adapt. The moment you change the input data set slightly or the downstream task slightly, all the steps fail. You have to re-optimize from scratch. You could use some learnings from the past, but you actually have to go start from scratch and build the whole pipeline. Now, you may be wondering that I'm talking about a very specific application in India. We have seen a lot of news articles that data science has revolutionized healthcare, finance, weather prediction, self-driving cars, and many others. We have seen a lot of news articles about these. The answer is yes. AI has been useful in all these scenarios, but what these news articles don't talk about is the amount of effort that the data scientists like us spend in training these models. We spend hours and days figuring out what is the right data set, how do we process it, and how do we train these models. So for this talk, we'll focus on a data science pipeline, the amount of effort that a data scientist spends in building this whole pipeline and not on the news article or what happens after that. So now let's go a little deeper into the data science pipeline and understand why these issues exist. So first, for data discovery, there are many tools nowadays like Google Dataset Search, where you can go search for data sets for your task. But all these tools rely on your domain knowledge or ability to search for data sets. And only if you can find those data sets, you will be able to use them. So if you don't know what data sets are useful for house price prediction, you probably cannot find the best data sets. For data preparation, there are hundreds of tools for missing value imputation, deduplication, outlier detection, and so on. The best method for your data set, no one tells. You have to try each of those methods, see which one works for your data set, fine tune their parameters, and through trial and error, you pick the best algorithm for data preparation. Similarly, for data analysis, you have to make a lot of assumptions about data distribution. And if your data does not satisfy those assumptions, your pipeline fails. So these are some of the reasons because of which the whole end-to-end pipeline fails, and it is highly brittle. The moment you change the input data set slightly or the task slightly, the pipeline will fail. And my research aims to address these challenges by building automated tools for data discovery that do not rely on your knowledge or your ability to search, but they automatically figure out what data sets may be useful for your task. Automated tools for data preparation, which do not require manual fine-tuning, but will automatically figure out the best parameters for your task or the data set. And robust tools for data analysis that can handle errors like distribution shifts, noise in the data, and so on. To develop these techniques, the two key questions that I ask are, first, how can we build adaptive data management tools that adapt with changing data distribution or changing tasks? Now, suppose I give you a magic tool that does that, adaptively figures out the best data set for your task, adaptively figures out the best pipeline that you should deploy in practice. Are you done? The answer is probably no, because as a data scientist, you would not trust this automated pipeline, what it is doing, why it is doing, and how can you fix it. So the second aspect of my research focuses on how can we make these tools deployable? How can these tools guarantee they're fair towards sensitive attributes? They explain what they're doing, what data sets did they choose, and why they're robust towards noise.
So just sort of an underlying assumption here is that there is knowledge or expertise that can look at these changed and adapting pipelines to say that, yes, there is ground truth and I know I'm better or I'm worse.
Not necessarily. So there's some guiding factor, but it may not be historical knowledge. You may learn it over time. I'll show you some examples. If it's not answered, we'll come back. Any other questions? So many of you may be wondering that data management has been there for 50 years. Data integration techniques have been there for 50 years. What is it that is new that I am doing that makes them adaptive? So just to give you a high level overview, traditional data discovery techniques were built to empower users to find datasets and not find datasets automatically. Similarly, traditional data preparation methods are considered as pre-processing steps where you do some kind of cleaning no matter what your task will be 10 years later. I am asking the flip question, which is, can we leverage the context of where these pipelines will be deployed to optimize them and build them in a better and optimized way? The kinds of context that I leverage in my work are of three types. First, where the pipeline will be deployed is excellent information to guide how you should build the pipeline. So for example, if I tell you I'm going to build a house price prediction model, you will automatically say school district should be used. And that's the kind of insight we have in this theme of work, where we leverage the downstream tasks information to guide data discovery. Second, in many cases, the downstream task is not very well known because a data scientist may be doing an analysis, and using that analysis, they'll figure out what tasks to do. For example, hypothesis testing, fact checking, where you don't know what's the reality and the analysis will help you. In those cases, we rely on the human's domain knowledge or expertise to guide the development of these data science pipelines, and the goal is to build better interaction mechanisms. Third, data science is very iterative. You often build data science pipelines on the same data set many times or changing data sets. So can we leverage information from historical executions to guide the development of future data science pipelines? So these are the three different ways I try to leverage context, some of which is historical information, some of which may not be historical information. To summarize, this slide shows some of the papers that I have in each of these things. The white boxes focuses on adaptivity, the blue ones on deployability. For the interest of this talk, I will focus on two specific themes. We'll start with building a data discovery pipeline to find the best data sets for a task. Then we'll try to deploy it in practice and see what issues come and how can we fix them. Before I go into the next part, any questions? Okay. So in the first part of the talk, we'll look at goal-oriented data discovery. Then we'll try to deploy and look at explainability and then some future work. So let's start with goal-oriented data discovery. In this case, we'll use downstream tasks information or goal information to guide what data sets should be used for your task. So just as a recap, we'll focus on house price prediction for this talk. You can assume we have a bunch of houses. We want to train an ML model which tells whether the house price is more than $1 million or less than $1 million. It's binary classification for simplicity. In reality, it may be a regression problem. So the data set in the US context would look something like this, same as what we saw earlier. I will generally show a data set with a yellow snippet, a prediction algorithm like this, the model as a tree for simplicity, and each model will be accompanied with a marker saying it's red, yellow, or green. You don't have to pay attention to the exact numbers. Now, given this initial data set, let's first define what are we trying to discover in this case. So here on the left, I show the initial data set. On the right, there is a data set that I downloaded from New York City Open Data Repository. This data set tells what is the crime in different neighborhoods of New York City. If you look at these two data sets together, you may notice that some zip codes in this data set are also present in this data set. And you can add a new column to the left one, which is the crime in the neighborhood of these houses. How to add this? This is called augmentation through database joins, because you're joining the two tables and then adding a new attribute to the initial data set. So for this talk, we'll focus on augmentation to initial data set through database joins. And we want to figure out what is the best augmentation for an initial data set. You want to discover these augmentations from data sets that are out there in open data repositories like New York City Open Data. To solve this problem automatically, there are many different challenges. First, there are thousands or even millions of data sets out there. You need to build techniques that can scale to those many data sets. Second, the different data sets are released by different organizations. They use different naming conventions. The formatting of these data sets may be very different. Your techniques should be able to handle the heterogeneity of format. Third, the different entities that share data sets, you cannot trust them. They may have a lot of missing values. There may be noise in the data. So when you integrate, you need to make sure the noise has been dealt with. Additionally, the schema information is also missing many times. You don't know what is the key column in these different data sets. So how do you figure out which data sets join with each other? So it's also not trivial to figure that out. And lastly, even if you solve all these problems, it's very difficult to find which of these data sets that you figured out as joining are actually relevant for your task. There may be thousands of different attributes you could add by joining this initial data set with others, but which of those are actually relevant? So these are the different challenges that we want to address. And to address these challenges, traditional approaches follow a two-step approach. First, what they say is, let's process all the thousands of data sets and create an index that is robust to noise. I will denote the index as a cloud here. What this index says is, if you join the initial data set with the red one, you will be able to add information about crime, where you will have to use zip code as the join key. Similarly, if you join the initial data set with the blue one, you can add information about cost of living, where you'll have to use state column as the key. So this index captures what can join with what. This index generally contains millions of joinable connections or edges in the graph. It's generally represented as a graph where edges denote which tables join with each other. Let's first see how good this index is in practice. So if you have 100 augmentations in this index, more than half of them are actually incorrect. The reason they are incorrect is you have to use heuristics to figure out whether two columns join or not, or whether they are key or not. The most common cases where these fail is categorical columns or numerical columns, where you don't know whether true, false, and 0, 1 are the same thing or not. So it's very hard to figure out the context, and generally these indexes focus on recall and not precision. And because of that reason, there are lots of augmentations that are incorrect. Amongst the ones that are correct, a very small portion of them are going to be actually useful for your task. And those are the green augmentations that we want to discover for your house prediction problem. And that's the goal. To find this green set of augmentations, traditional tools say, let the user search using keyword search, for example, Google dataset search. You can go type in information and find relevant data sets. So let's look at an example of that. You go to Google dataset search, you say, find me data sets about cost of living index. You get 80 different data sets. You'll have to download each of them, then figure out whether they join them, see the quality, missing values, train the model, and then decide whether you want to shoot another query to dataset search or not. Another option you have, you call a domain expert, ask them what data sets you use. Domain expert says school district information, use that information, go back to dataset search, find that information, download it, and go about it. So after these many iterations, you're probably done using traditional methods. You've trained a model, but there's one question that will always bug you. That is, you did not explore all possible datasets that are out there. You could only search for datasets that you knew are relevant for your problem. So can you do better than this? There may be thousands of datasets that I did not look at. And that is the question we want to answer through this work. How can we give them the confidence that we have explored all the datasets and you have found the best datasets for your problem? Any questions about this?
Yeah, what I'm curious about, one thing that wasn't on your list of challenges was what's the right join?
Yes.
By which I mean,
The correctness of it.
well, so imagine you've got a data set that has stuff by zip code. And you can translate the zip code into a polygon. Right? We have another data set that has stuff by neighborhood,
Yes.
not zip code. That's also a polygon, but you could still.
Overlapping or something.
Yeah.
So there's some work that focuses on that. I can come back to it.
Okay.
But our technique supports it.
So along the same lines, it's possible that you probably have some uncertainty, but also some different ways of representing the same thing
Yes.
across these data sets that you didn't know about until you actually
Found.
went through each of them or had somebody with the knowledge to.
Yes. So what
that's it.
I will show that a quick teaser is our approach will find data sets that are useful for the task. They may not seem useful to a human. Human has to still go back and validate. We are not removing a human out of the loop. So what we are saying is if there are thousands of data sets out there, this tiny fraction of those 1,000 are actually useful for your task. Now you go look at those. You don't have to search through those 1,000. So we are reducing the search problem from those 1,000 data sets to a number like 10, and the human just validates those. I'll show you some examples and we can come back to it also. So let's first see why traditional techniques failed to solve this problem. What is it that they were missing to solve this problem? So let's go back to the problem. What we know is we have an index that has millions of attributes that capture which tables join with which ones and what new augmentations you can add. What we also know is we want to use these data sets to train a ML model. So all the data sets that we discover will go to an ML model and we can tell how good this model is because we have some validation data set. And this piece is what traditional techniques did not assume and did not have access to, and because of which they could not automate. So the key question here is, can we leverage access to this prediction algorithm to figure out what data sets in this cloud are going to be relevant for our task? Now, you may say, this is sounding very much like feature selection. Why can't I go back to this index, find all joinable data sets, create a giant table with all the different columns or different features, do feature selection, and I'm probably done? The answer is yes, this is a valid approach, but it has some issues. First, adding millions of different attributes requires materializing all those joins, which is not cheap, it's expensive. Now you'll say, I'm rich, I'll throw a lot of compute at it, I don't care about it. Even then you can't solve the problem because there are three requirements. One is you should be able to handle any task. You need to be efficient and effective at the same time. You can't get all three of these at the same time because of the curse of dimensionality. The data set is few set of rows, but having millions of columns will make it impossible to tell which of those attributes or which of those features are actually useful for your task. This is not a very viable approach. Now you may say, what about LLMs? LLMs can also probably give you some information. They know the knowledge about what is important for house price prediction. The answer is probably yes, you could do that. But with that approach, you cannot figure out whatever is not a common sense knowledge. If that information is not written in some text, LLMs cannot figure it out. Also, even if they can tell you about some attributes, the attributes that are useful for your task depend on the task information and the data distribution. It's very hard to capture data distribution characteristics when you query or prompt an LLM. And lastly, the cost is also a challenge. There are millions of different attributes. You can't query LLM about each of those attributes. But it's a very valid direction, and there is some future work that I'm focusing on combining LLMs with the current approach. But for this talk, you can safely assume we'll not focus on LLMs to help with data discovery. Now, let's define the problem more formally and see how we can solve it. So we are given an initial data set D, a set of attributes gamma denoted by that cloud, which is an index, and a task implementation T, which is the prediction algorithm. We know that this prediction algorithm takes any data set as an input, returns a model. We can tell how good this model is. Given these three things, we want to find a set S such that when you join D with S, and then you calculate the utility over the task P, that is maximized. So you want to maximize the utility of task P over the initial data set joined with this set S. There are some constraints. The S must be a part of this index. The size of S must be small because if S is too large, you are giving human too many data sets to look at. That's not good. S should be minimal. It should not contain any attribute that is not useful for your task. So these are the constraints. And this is like an optimization problem equivalent of the problem we are trying to solve.
So are you assuming right now that S or I is clean? Like in the sense that the match and join can actually happen?
Yes, we are assuming that the gamma has figured out all the joins. It may not be clean. It may still have noisy attributes.
No, but joinability, like let's say I'm trying to join in a field and the references and the way you sort of refer to different
So-
things is different.
So we assume for the next part that you have figured out how to join.
I see, okay.
You just have not figured out whether it's relevant for your task or not.
So I wonder, it looks like the way that you're doing this is that you're starting from the join and then the decision if this join is useful.
Yes.
I wonder if the reverse would lead to a similar result, which is I would decide which features would be relevant to the task. And then I would have a smaller subset that I would join. And then I would do the test again.
So for your approach, we would need to know which features are useful for the task, which is not possible. Because how would you know which features are useful for house price prediction until you join?
So your example, for example, with zip codes, I wouldn't know that by just the feature alone before I join it, or let's say with.
So
the
zip code I may know, but like school district information, there's some examples I'll show of attributes that a human would not know of when you start with the problem.
I see.
So you generally don't know about which features are useful for, say, drug addiction prediction. In that case, you have to rely on the data to tell which attribute should I look at. So that's the main reason. Yes.
You said S needs to be minimal, which means like, could you explain that again?
So if you drop any attribute from S, you will get a worse model.
And so how do you know that like ahead of time? Or like, how do you know that it fits the
We
constraint?
don't know ahead of time, but the final result needs to guarantee this.
Okay.
The final set is.
And is that worth like, is that like, okay, I see.
So this is an optimization problem. So if you are good at optimization problems, you could solve it by enumerating all sets S of size less than or equal to K, train an ML model on each of those sets, pick the best model, and you'll probably be done. You will get the optimal solution that is guaranteed. The issue is you would have to train the ML model into the K times. I call it queries because I don't care about what you're training. So you train the ML model into the K times, which is not good because N is generally in the order of millions. And even if K is 2, it's not feasible. But what this approach tells us is the optimal solution is somewhere in between these N to the K options. If we could prioritize these N to the K options in some way that we will hit the optimal solution first or faster, we are probably doing okay. So building on this insight, what we also saw is that similar data sets often have similar utility. So just to consider an extreme case examples, if two data sets are exactly the same, training an ML model on D1 or D2 will give you the same utility. So there's no point in training on two data sets separately. So using that insight, what we did was we clustered the initial set of data sets based on certain properties. I'll tell you how. And once we have these clusters, if we diversify the search across these different clusters of data sets, we will probably hit the optimal solution faster. Now the question is, how do we cluster these data sets and which clusters do we choose? To cluster these data sets, we generated different features for different attributes, which are also known as data profiles. So for example, if you join these two data sets and you add information about crime, how does this new column look like? How many missing values does it have? What is the correlation of this attribute? What is the mutual information of this attribute and so on? So using these data profiles, we clustered these different attributes and got a bunch of clusters. Now, if I give you these clusters, the question is, which cluster should we pick to reach the optimal solution or a good solution quickly? It would have been an easy problem if you knew how good a cluster is. What I mean by that is, what is the probability if I sample a random point from this cluster, it will help me with the task. If I had given you this probability, you would have probably used these probabilities to sample based on clusters. In reality, you don't know them. To estimate these probabilities, you have an explore-exploit dilemma, where you can either choose different clusters to get an information about different clusters, or you could go deeper into one cluster, ask many queries from one cluster, then go to another one, and so on. To solve this explore-exploit dilemma, we used a bandit-based approach, which is not very surprising. So I'll tell you more about how the bandit-based approach works. First, what it does is it initializes each cluster with an equal probability. So there are 4 clusters, 0.25 each. In the first step, we sample a cluster based on probability values. And suppose we chose this new attribute from the first cluster, adding this attribute, trained the model, tested it, did not help. It's still in the red region. Use this information to reduce the likelihood of the first cluster, renormalized it, the likelihoods of all other clusters went up. Use these probabilities to sample again. This time we chose something from this cluster, the green attribute. It had improved the accuracy. Use that information to increase the likelihood of this cluster, renormalize and proceed. After some 100 iterations or so, the cluster scores have converged, and the guarantee is these converged scores actually capture the probability that we wanted to start with. So with this approach, we will be able to get a good idea about which clusters are good and which clusters should we sample from. In summary, so this is a bandit-based approach that first clusters are different data sets and then looks at different clusters to pick the best attribute. So the good thing is it uses data profiles to diversify the search. The bad thing is, in the worst case, it may have to look at all possible cluster combinations, which is number of clusters choose k. So the worst case complexity of this approach is still pretty bad. It's only good if your clusters are reasonable, if your data properties are good. Question?
Yeah, I had a question about the reasonability of clusters. Is it guaranteed that they'll be destroying? The practice there could be significant.
There could be noise, and we have mechanisms to deal with noise. So if a cluster does not look very homogeneous, we tend to break it.
So you ensure that the
Clusters are disjoint, yes.
Another question about clustering. It sounded like you cluster based on like metadata about the data sets.
Yes,
So there's not necessarily semantics taken into consideration.
the distribution of this data also. It's not just the metadata. So the distribution of the post join is right. So just to summarize, this is the first approach, some advantages, some disadvantages. Major disadvantage, highly inefficient in the worst case. Additional property that we noticed.
So quick question. So you're using this in the context of your own data, right? But let's say the clustering was based on whatever criteria it is, because you have to sort of consider joinability as well, right?
So the joinability is considered by the index. So we divide the problem into
Also,
two parts.
first you do the index-based joinability. How do you know that? How do you know what?
So it's
will-
approximate. That's why I showed you the quality of the index. So the index that we constructed is going to be approximate.
Okay.
And the goal is to find the attributes in that index that are correct and useful. And I'm not guaranteeing I'll find those. I will find something from this. You'll see it later on. But for this talk, I'm not focusing on how do we tell whether it's a join or not. I assume you are given this. Now you're just checking whether it's a relevant join or not.
So they're all joinable at this stage. You already
Yes,
know that.
yes.
So
Many of these questions will be answered soon, so just. So just to quickly go over the second approach. What we also noticed is the utility metric that you are trying to test on often satisfies certain properties like monotonicity. What I mean by that is, if you add more attributes, your utility should always go up. If it does not go up, just don't add it. So you can always write a wrapper on top of your utility metric to guarantee monotonicity. Additionally, many different metrics satisfy submodular property, which is also known as the law of diminishing returns. just to look at it, if you add an attribute X to a bigger subset T2, the marginal gains will be lesser than adding the same attribute X to a smaller subset T1. And whenever these two properties hold, the greedy algorithm is known to give us the best solution. It's not going to be the optimal solution, but it's a constant approximation, which is probably the best you can get in this case. So we used these insights and combined it with the clustering approach, which looks something like this. We start by clustering the different attributes and then greedily chose the best cluster for your task. Advantage of this approach, highly efficient, linear in the number of clusters, but it can fail when the utility metric is not submodular or it is supermodular. So it also has some disadvantages. I showed you two techniques, one which works in all cases but can be inefficient, another one which is highly efficient but can fail sometimes. To get the best of both, what we do is we run them in parallel. Let the greedy pick one data set, let the bandit-based approach pick one data set. Whichever finds the best data set first, we stop. So if the utility metric is submodular, the greedy will be fast, we'll stop. If the utility metric is supermodular, the bandit-based approach will win and we'll stop them. So combining them in parallel gives us the best of both.
So, clarification, utility is the end accuracy.
Yes, it could be the accuracy, it could be some other task you're solving. In this case, it's accuracy of the ML model. So just to go back to the initial pie chart, I showed you that if there are 100 augmentations, most of them are incorrect, some are correct. We want to find what is correct and useful. What our approach guarantees is it will find attributes that are correct and useful, but it may have some false positives. What that means is it may return certain attributes that are actually not correct joins, but are still, the ML model thinks they're useful just by chance because of sampling issues or data quality issues or so on. But the hope is the false positives are going to be very few in practice, and those few data sets the human can quickly check where they want to keep it or not. They don't have to deal with millions of data sets. In the interest of time, I'll skip over the theoretical guarantees that we have, but I'm happy to talk about it after the talk. Let's quickly look at the experiment results. So to test this approach, we downloaded data sets from different open data repositories like Chicago Open Data, New York City Open Data, SF City Open Data, and so on. Created a collection of 69,000 different tables with 3 million columns. What that means is we could potentially add 3 million different attributes to the initial data set. May not be realistic. Sometimes they may not make sense, but potentially we could. It had around 1 billion rows, around 120 GB. We downloaded a data set from Redfin to predict house prices without doing any augmentation. By using the attributes of the house from Redfin, the accuracy of the model was 0.6 max. By combining it with this corpus, we were able to get up to 0.84. So you're seeing a 15% improvement in the accuracy. And our approach took 6 minutes to find the data sets. Now, we went back and checked how good are these data sets? What are these new data sets? Some of them were very obvious ones like school district information, but there were some surprising ones, and let me show you two of them. First, taxi trip data was useful to predict house prices. So higher the taxi trips from your area, probably more expensive house. It was not obvious to us initially, but probably makes sense because if your house is in the downtown area, more people take taxis there, so the prices are also higher. It's not a causal relationship, but it's a correlation. Second, distance from grocery store is predictive of house prices. This was also not very obvious to us, but there are studies that have shown that whenever Walmart comes to town, house prices go up. So these are some attributes that we were able to discover from the data set automatically, which we would not have been able to do if we had relied on the human's domain expertise or the human's knowledge. And this is the power of automating data discovery.
So I still have a question, Simon, the part I was asking. So you said you downloaded 3 million or whatever the number of tables were, right? But they were all joinable. How did you figure that out?
All were not joinable, but we constructed an index which had around, I think, 3 to 10 million of images.
So but that's, the 6 minutes is not counting that effort, right?
No,
Because that would be
So-
a very
Yeah.
major effort.
so 69,000, 6 minutes doesn't count the index construction.
Yeah, because
That's
that-
offline.
That's
Yeah.
all.
It takes around 4 hours for that.
Okay, yes.
So the
That-
index
that worried
construction
me.
is offline, yeah. Okay, so I have around 15-ish minutes, so let me quickly go on to the next part. So this is the algorithmic solution of how to find relevant data sets for your downstream task. In addition to these algorithms, we are also building an end-to-end system design where the human does not have to just specify the task as a black box, but they can also interact with the system about the domain knowledge they have. So if you know school district information is useful, just tell it to the system and not let it find it on its own. This work, we have been collaborating with a lot of different places. First, we have been working with U Chicago Booth School to find causally interesting attributes where we look at spatial temporal joins. So two things happening close by have some causal relationships. So for example, whenever you jump a signal, there are more chances of accidents. So the accidents in a location and the number of signal jumps are correlated. So how can you find such interesting correlations from the data? We have been using these tools with IBM to build the AutoML tools, where the focus is, I want to find these attributes, but these attributes should be meaningful semantically. Many of these joins that we found may not be semantically meaningful. We've been working with German Cancer Research Center to find interesting attributes that are predictive of cancer and so on. Additionally, recently, Infosys has been interested in figuring out whether there is any PII leakage in the data or not. How can you find data sets that join and let someone get in some PII information from the data? So here, we are looking at complex joins like joins with transformations. Then we are working with Irvine Eye Care to figure out data sets about similar patients in your repository. So for example, you are a doctor, patient comes to you. How can you figure out other patients that had a similar symptom so that you can look at their diagnosis to guide your diagnosis and make sure you are equitable to the different patients? Then we are working with Google to figure out what's the best data set to fine tune large language models. This is more towards machine learning and less towards system learning. And finally, we are also building an end-to-end marketplace for data sharing, where a user can say, take my data and share it with others, but don't leak the data, let them train ML models on my data. That's the kind of the marketplace you're looking at. There are some other additional challenges that many of you already mentioned that we are looking at. So for example, how do we figure out these two data sets join? If you just look at it superficially, they don't. But in reality, they do. If you convert this location to the zip code, time to quarter, and now if you look at these two data sets, you will say they do join. So how do you automatically figure these out? Then federated settings. The data sets may not be available to you on day one. You may have some statistics like the distribution of the data or a histogram of the data. How can you use these information to figure out which ones are relevant? Because many times you have to pay the price to get the data. So can you figure out which is a relevant data set just based on these summary statistics? Many times the utility metric is not available to you. You can't train an ML model all the time. In many cases, it's very expensive to train an ML model, which is the case with large language models. Can we do something better there? And lastly, we're also building a programming language where the users can specify declaratively what task they want to solve, and the system will figure out what data sets are relevant. In some sense, you can think of it as a user writes a SQL query without knowing the schema, and our system will fill in that SQL query with the schema information for the user. So to conclude this part, I showed you how traditional techniques cannot find relevant data sets for your problem, but you can automate it if you have access to downstream task, which was an ML model in this case. Now in the next part, we'll try to deploy this model in practice and see what issues can arise. So now we have a model that takes details of a house as an input, tells whether the price is more than $1 million or less than $1 million. We shared this model with a domain expert. the domain expert gives two inputs, A and B. A is more than 1 million, B is less than 1 million. But the domain expert is confused because they thought B was a fancier house. Why is the model saying it's less than 1 million? And that's something they were confused about. Another question they may ask, would it have helped if I had added additional room to house B to make its price more than $1 million? So these are the questions that domain experts often have about the ML models or the data science pipelines. And let's try to answer one such question, which is, what is the probability that the house price will be more than 1 million if we add an additional room to this house? You will say it's a very simple question. Let's just change the input from 5 to 6, pass it through the model, we'll be done. This is the wrong approach, because if you change the number of rooms, you may potentially change the covered area, which may affect other attributes. These attributes you can't change independently. There are some dependencies that you need to look at before passing it to the model. Now you may say, data already captures it. Why can't we look at the data to answer this question? Valid approach. Let's look at that. So for this approach, let's assume there are two zip codes A and B, and the data looks something like this. If you look at houses with only 5 rooms, the green shows more than 1 million, red shows less than 1 million. 60% of them have price more than 1 million. If you look at houses with 6 rooms, 40% have price more than 1 million. If you look at the data, it looks like adding a room is not helpful, and that's the conclusion. Now, let's look at the same data at a different granularity level. We're looking at the data now at zip code level. If you focus on zip code A, 0% here, 25% here. It looks like if the houses are in the same zip code A, then adding a room is helpful. Now let's look at zip code B. In this case, 75% in 5 rooms and 100% for 6 rooms. It seems adding a room is helpful when you focus only on zip code B for your analysis. What this means is we got contradictory outputs based on where you analyzed. If you analyze the whole data set, adding a room was not helpful. But if you analyzed at zip code level, adding a room was actually useful. And the reason this happened is called Simpson's paradox. And the reason it happens is because zip code is a confounder for this relationship between rooms and house prices. And because of this confounding relationship, you cannot analyze this query at the whole data set level. You have to analyze at the zip code level to get trustworthy insights. And traditional methods to generate explanations for ML models, here's a summary of them, some of which were co-authored here, at UCI also, do not capture these causal dependencies, and because of which they are not robust. You cannot rely on their insights. What we showed in our work was, if you have access to the causal dependencies between the different attributes, you could leverage this information to figure out which attributes are important and how to answer these questions. Specifically, the probability question that I asked initially is mapped to a counterfactual estimate from causal reasoning, which looks mathematically like this. I don't have much time to go into it, but the key takeaway is this mathematical equation can be estimated from the data. And what we showed was you can approximate it like this. So you don't have to pay attention to the formula. The score that I showed you is called sufficiency score, which is bounded by these two values. Further, we showed if the data has certain properties like monotonicity, these bounds converge, you get the exact value, and we have also recently improved on. Let's look at some empirical results to understand what is the implication of this. Again, house price prediction. On x-axis, we have the different attributes: zip code, police station, number of rooms, crime, school district. Y-axis is the importance of each of these features for your task. Based on our approach, zip code is the most important feature because the moment you change the zip code, you change the crime information, you change the school district information. So it has the maximum impact on your house prices. The ground truth in this case matches our insights. SHAP is a Shapley value-based approach, which does not capture the causal dependencies. It says zip code has zero importance because zip code is not used by the model. So if it's not used by the model, it's not useful. And these are the insights that are misleading, and it just says crime is the most important attribute. So these are not very actionable insights that you could use and implement in practice. The same is the case with feature importance, which also thinks zip code has very low importance in this case. So this is just one example where causal reasoning techniques are extremely important to get insights that are actionable and reliable, and humans can relate to them.
So the causal
Graph.
graph was sort of an input given to.
Right now, yes.
Okay.
Right now, we assume it's correct also. But there's this work which assumes.
I was going to
Relaxes.
ask you, like, how robust is the technique in case you.
So what
you
we
know,
tested
recapture
was,
graph?
suppose you assume it's a complete graph. You get better results than having no graph. So the graph is still helpful,
I see.
but the better you know about it, the better you can do. Okay, so to conclude this part of the talk, in the first part, I showed you how context information can help you build better data science pipelines. In the second part, I showed how causal reasoning is extremely important to get reliable explanations. Now, in the next 2 to 3 minutes, I'll quickly talk about some future work. The key goal of my research is to build tools that will help us enable people who are not real coders to build data science pipelines. People who are Microsoft Excel users, business intelligence tool users, who can't really build these data science pipelines or don't have the domain expertise to build them. To do that, the 3 key pillars of my research are: first is effectiveness. I aim to build tools that are correct and easy to use and are robust to noise. Efficiency. These tools must have low running time. They should be easy to deploy. A data scientist should not spend hours building these pipelines. They should be doing it in a minute or so. These should be equitable. There should not be any unwanted biases. If there is any unwanted bias, it should tell the user what it may be and let the user decide how they want to fit. Here are some keywords of the things that I worked on, and I'm happy to talk about any of those after the talk. But 1 or 2 problems that I'm excited to work on next is in the data discovery aspect, can we leverage information that is not just in tabular data, but also in the form of images, books, videos, and so on. Traditional tools focus on extracting information first and then supporting it through data discovery. But if you combine the loop where you extract only when it's useful, you can do much better and you will not waste your resources in extracting things that are not actually useful. Second, suppose I tell you, build a pipeline that maximizes the accuracy of the model. Can you automatically figure out what data cleaning steps to take and in what order you should implement them? So for example, should you do data imputation first and then duplicate detection, or transformation first and then data imputation? What should be the right order? What should be the right subset? What should be the right set of parameters? How can you build these automatic data science pipelines automatically? So with that, I will stop. I just want to thank my collaborators, and I'm happy to take questions now.
So thank you for the talk. We have time for a few questions.
Oh, sorry, just so very quickly. So you mentioned in the first part of the talk that do you actually have you mentioned a runtime of 6 minutes.
Yes.
Did you have to train a machine learning model within that time, or how were you testing this?
So the question is, in the first part, did I train the ML model in 6 minutes? The answer is yes. We did not train a complex neural network. We trained a small proxy random forest to guide the search. Once we figured out the relevant data sets, then we gave all the relevant data sets to a more complex model.
And how do you know, so I guess the question then is how do you know, if the random forest is capturing, say what a neural network would capture?
So the expectation is if a weaker model captures information, the stronger model will likely find it useful, or it may just throw it out. So it's like a 2-step approach. Any other question?
These hypothesis testing would be cheaper instead of a smaller model.
Sorry?
Like doing hypothesis testing on the feature wouldn't be cheaper than small model. For example, just take the regression and see like the FS statistics of these two features.
So if you have to build the regression model on all the features, you have to materialize all the job costs, which will take a lot of time to materialize. And then there's a cost of dimensionality because you have millions of attributes, various sizes.
Replacing that the small machine learning that you mentioned with just hypothesis test isn't that possible?
So that is possible to figure out whether a feature is useful or not. Yes.
In the interest of time, we will take one last question. Go ahead, please.
So have you considered like, for example, in your experiment, you have 3 million of columns. So what if like eventually you choose 1 million of columns that can achieve utility like 0.8, but with 1,000 of columns, you can achieve 0.78. Then in that case, so the utility decrease not that much, but efficiency of training the model would be increased.
So you're actually hitting one of the weaknesses. So one of the issues with our approach is it can tend to overfit. Because when you add more attributes, it could overfit and that's not good. So we are extending our work to find diverse set of combinations where some of them may overfit but others don't. And let the human decide or some other context information to decide which is a better solution. But in this work, we did not do that.
Okay, so one last announcement is that we have a student roundtable at 3 p.m. at DBH 2065. So if you're interested in asking more questions, we'll hold it over there. So yeah, thank you so much.
It's like the whole thing.
The checking code is context.
What is the context of this?
What's the context?
我比较晚，有 capital C。他在讲一个什么？就是讲一个什么？
Some of it is.
You know that Prathy has been bothering me in quite a bit, getting asked to study.
Yes.
It's good. Let's see what comes out of it. So we'll soon see them.
David definitely.
Very much.
We have multiple.
I think what's the plan? Dinner. If you can make it.
那其实他没有遇到一个问题。你推荐你的新的 data set，这个新的 VR model 能不能降低？
Questions.